for engineers and how engineers use Mathcad in their design work and analysis work and so on. We'll also talk about how Mathcad and Creo work together. So Mathcad and Creo are integrated. They're very tightly connected and tightly integrated. And so we'll take a look at how that functionality works as well. So going back to the top, Mathcad, or PTC Mathcad, is essentially an engineering notebook. It's an electronic engineering notebook, and it runs on Windows, so it runs on the Windows desktop. And it's intended to give engineers a very natural environment to be able to do their engineering calculations. So that being said, it's very different from other applications that engineers might be using for calculations. It's different from spreadsheets. It's different from programming languages. And the reason that it's different is because when we're working in Mathcad, we're essentially working within a notebook kind of environment or a document kind of environment. So this slide is basically saying that Mathcad gives you, the engineers, the ability to analyze mathematical calculations, solve things, document what you're doing in a way that's intuitive and easy and natural, and then also to be able to share and communicate that information to others, whether you need to share internally or externally. Just being able to communicate your engineering work and your engineering intentions and your assumptions and decisions in a way that's easy to understand and in a way that's transparent is very important. So these are the things that Mathcad brings to the table for engineers. Okay, and it'll all make more sense when we take a look at what Mathcad actually looks like. So going to the next slide here, this is a screenshot on the right of a Mathcad document. Okay, and so we call these Mathcad documents worksheets. So I'll probably use that term interchangeably, documents, worksheets, it's the same thing. So this is a Mathcad document on the right, and the things that you'll notice here are that everything is very readable, it's very transparent. So any engineer can look at this document and understand it, dissect it, analyze it, question it, talk about it, because all of the math is presented in natural math notation. Okay, so that's one of the key differentiators between Mathcad and other applications that are used for calculations. All of the math is represented and captured in natural math notation. And the document itself is a whiteboard. So anywhere within this document or this whiteboard structure, we can enter in content. So we don't have to write our calculations or do our engineering work in a structured environment. There are no rows, there are no columns, there's no grid, there's not a programming box. It's a whiteboard. So we can enter in any content we want, whether it be math or text or graphics or plots or images. We can enter in any content type we want, anywhere we want in the document. Okay, so the document, it's comprehensive. So it combines math, text, graphics, like I just said, but the math is all live. So beneath the surface of the document, the math engine is running. And so if we make a change to a design variable or an input variable that's driving a whole sequence of calculations, if we make a change, that change is going to propagate forward and update everything that depends on it down the line. So it's a live document. Okay, so any change that we make, whether it's to a design variable or a formula or a function, any change we make is going to update all of the dependencies that rely on it. Okay, now the math engine itself, there are two components to the math engine. There's a numeric math engine and a symbolics math engine. Okay, so we can evaluate things numerically for numerical results. We can also evaluate things more analytically in terms of variables if we need to. And probably one of the most important things about Mathcad is that it's units intelligent. So Mathcad has a built-in understanding, a built-in library of units, and we can include those units on our variables, in our equations, in all of the calculations that we do, and all of those units will be managed and handled and carried through calculations properly. Okay, so Mathcad also understands what the dimensional compatibilities are between units. So if we're trying to do something where the units aren't dimensionally compatible or things don't add up correctly, it's going to let us know that we're making a mistake when it comes to the engineering units. All right, so these are some of the things that we've already talked about. Okay, so the document itself is intended to be shared, and it's intended to provide an environment where we can capture our intellectual property in a way that can be reused, communicated, shared, discussed, and so on. Okay, so because of that, the application has a document-centric environment to it. Okay, so we can create professional-looking documents. And then it's very easy to learn how to use. We use the ribbon architecture for the user interface. It's very easy. It's very intuitive. And then the Math Engine also has quite a bit of advanced math exploration functionality. So it's a very deep math engine. It's both broad and it's very deep at the same time. So some of the advanced math functions that people may not expect are in fact included in the math engine. Okay, so things like data analysis, statistical analysis, curve fitting, curve smoothing, probability, all of that's available through the math engine. Okay, so a couple of things before we go into the actual application that we've talked about that we just want to summarize here. All of the math is captured in natural math notation. Okay, so we don't have to write any programming. We don't have to do any scripting to use Mathcad. Okay, we write the equations and the math down just like we write it in our notebook, just like we see it in a technical publication or reference. Okay, and so on this screenshot here on the right, you can see this differential equation using prime notation. So that's what we mean by standard natural math notation. And so all of the math goes in that format. Okay, there's comprehensive support for units, which we can also see here. We see units of kilograms, newtons, newtons per meter. We see units of meters per second. So all of those terms, variables, inputs, they're included and defined with their units. Documented oriented approach to engineering, just like we would in our notebooks. It's visual, and we can connect it to Creo. So we can do some design work in Mathcad, and then we can drive geometry in Creo automatically by sending results from a Mathcad worksheet to a Creo model. Okay. All right, so let's go ahead and go into Mathcad. So I'm going to update your screens, and you're going to see Mathcad loaded with a bearing shaft document. So this is a completed Mathcad document. So let's just look at a couple of things that we just talked about. So this is the completed document. Now, when we're starting a new document in Mathcad, it's going to be blank. It's going to look more like what we have here, just a blank document. So there's a math engine running underneath the surface of this document. And so if we want to type in words, text, graphics, we can just type those in. So if I wanted to type in, this is the calculation for volume, okay, I'm going to type that, and then here I'm going to put a math expression that calculates some sort of volume. So here, I'll just put in the definite integral, okay, and I'll just say this is going to be the sine of t squared times 17 t dt. And then we can integrate that from 0 to pi and type equals, and there's a numerical result. Okay, so we have text, we have math. Now, if we wanted to parameterize this, we define a design variable above where we need to use it. So the math engine processes information from top to bottom or left to right. So there we'll define a design variable n, and then instead of raising t to the second power, we'll raise it to the nth power. Now when I hit enter, that number 4 is going to get substituted and the numerical result will update. Okay, and then we can assign this to a variable called volume. So in Mathcad, we use meaningful variable names. We don't reference numbers. We won't reference this result 5.757 by location. We reference by variable name. Okay, so now to use that 5.757, we're going to type volume divided by 3. And we can assign it to a variable here on the left called volume subscript new. And then we can display it in a separate area if we want to. Okay, so this is how we build out these documents. We integrate math, text, graphics, so we can capture our assumptions as we're doing our work, our decisions as we're doing our work. Why did we multiply by 17 here? That's kind of a random number, so we'll just make a note. Multiply by 17 because. So as we're doing our work, the point is as we're doing our work, we're capturing our thoughts, our assumptions, our decisions, so that that information doesn't get lost. It doesn't get forgotten because it's easy to do it as when we're working in this document environment. So that's what starting from scratch looks like. So now let's hop back over to the document we were just looking at, this one, and let's walk through it. Okay, there's a lot going on here, and we're going to start with the basics, and then we'll take a look at some of the more advanced functionality. After this, we'll do a spring design, and then we'll connect all of this up to Creo. So here we have a bearing shaft, and the problem that we're trying to solve is that we want to calculate the critical shaft speed of the shaft bearing. Okay, so this is an image from Creo. Okay, it's pasted in, so we can just paste our graphics in. We can browse for them and drop pictures into these documents. And so that's a CAD part. Okay, that's just been added here to the document. Now here we have some inputs. We have Young's modulus, 210 gigapascals, the outer diameter of the shaft initialized to 15 centimeters, the inner diameter initialized to 9 centimeters, the mass, 15 kilograms, and the shaft length, which is the sum of these A and B parts here. Now notice the use of units. Okay, we've defined the diameters with units. We've defined the mass with units. Okay, so when we sum A and B, A is 50 centimeters. If you follow my cursor, I'll just highlight these. A is 50 centimeters. B is 50 centimeters. When we add those together, we're going to get an answer with units of length because our design variables have units of length. So if we type A plus B and type equals, we're going to get 1 meter. Now, we're in the SI system here. Okay, so every Mathcad document has a unit system associated with it. So if you follow my cursor over here, the unit system is set to SI. Okay, so we can change that to the US customary system or the CGS system. But being an SI, that means our answer is going to be given to us in meters because meters is the default for length in SI. So that's a little bit about how the units get calculated. Okay, so whatever unit system you're in controls how your answers get returned to you. So if we were in the US customary system and we summed A plus B, we would get an answer in feet. Okay, now we have the answer in meters, okay, by default, but we can certainly convert that. We're pausing here before we go on to talk about units for a minute. We can certainly convert that answer to a different unit of our choice. So meters is the default, and that's fine, but if we want to see this in any other unit, we're just going to replace the meter with the name of the desired unit. So if we want to see that in feet, we'll type FT. Even though we're in SI, it's okay. Even though we're in SI, we can still go to feet. Okay, if we want to see it in inches, we'll just replace that with inches. Okay, and now there's the answer in inches. So the default will be in SI of meters, but then from there, we can go to any unit we want, okay? Now, all of these unit conversions, they're built in, okay, and they're very, very precise. So there's no round-off error. They're very precise. all of the calculations in Mathcad, including the unit conversions, are done with 64 bits of floating point precision. Okay, so it's very precise. Now, all of the units are located in this drop-down list. Okay, so this is where you can come browse and look at the different units that come with Mathcad, different units that you might want to use on your variables and in your calculations, units of flow rate, force density. So these units are assigned to dimensions, and then under each dimension, you can see the itemized list of units available. Okay, so if we go to length, we can see here feet, we used inches, okay, we used centimeters. So that's where these units are. All right, so let's move on. So we have our inputs, the outer diameter, the inner diameter, the mass, the length of the shaft. Now we're going to calculate the speed. Okay, so this is pretty straightforward. It's 3 calculations. First, we calculate the second moment of area, okay, and we expect units to the 4th power. We know that that's what the units should be. So the calculation is pi over 64 times the outer diameter to the 4th power minus the inner diameter to the 4th power. Okay, so to type that, it's pretty easy. I'll just go to the right underneath our image, and I'll just type I, and then we'll just type pi divided by 64. And the reason I'm doing this is just to show how easy it is to build this out. So outer diameter to the 4th, subtracting the inner diameter to the 4th, and that's it. That's it. So then we can tack on an equal sign here if we want to, or we can do it separately. So if we type I equals, we're going to get meters to the 4th power, again, because we're in SI and meters is the default. But let's change that to centimeters to the 4th power. And that's exactly how we build this calculation here, okay, for the second moment of area. So from there, we can calculate the stiffness coefficient, CQ, and from there, we can calculate the critical speed, okay, in radians per second. So now, if we change any of these inputs, if we change the outer diameter to 17, our critical speed is going to update. So I'll hit enter now, and now you can see our critical speed updated. So we can change the inner diameter, and we could proceed to change our inputs and look at our results, okay? So now the next thing we're going to do is iterate over a combination of outer and inner diameters, right? We could sit here all day and we could change outer diameter from 17 to 18 to 19 to 20, but we don't want to have to do that. That's going to take a lot of time, and then we're going to have to assess our results and so on. So what we want to do is iterate, do everything at once, and then build a summary table of results, okay, for all the combinations of diameters. So I'll scroll to the next page, okay, and on the left is what's called a Mathcad program, and that's what we use to iterate. And on the right is a table of inputs in yellow, okay? So that's an input table of input data, okay? And so if we go to the Matrices and Tables tab on the ribbon, that item is this one here, Insert Table. So when you insert a table, this is actually pretty useful. If we insert a table, it looks like columns, just like in Excel, it's columns. And we can give, but the difference is we can give this column a meaningful title. So if I call that one D and put in the units as centimeters, I'm sorry, uppercase D, and then the right column would be lowercase d and give it units of centimeters, then we can type some numbers in here. Now we've created very easily and very quickly an input table of test cases. So the difference is that in Mathcad, that table is intelligent when it comes to the headers. So capital D is the name of a vector that stores the left column, and lowercase d is the name of a vector that stores the right column of inputs. Okay, so now we can iterate over those two vectors or those two columns of input data and calculate the shaft speed for every combination of diameters. So that's how we create that input table. Now on the left, this is the Mathcad program. Now any engineer can program in Mathcad. You don't have to have a programming background or a programming pre-existing skill set. You don't have to know VB or JavaScript or C or C++ or Python. Any engineer can do this, okay, because you're basically going to click on things from the ribbon and fill in the blanks. And inside the program, we use natural math notation. Okay, so here on the Math tab, there's a programming button. To start a program, you come here and you create a new program, and then just click on the first line. And if you want to do a for loop, you'll click on this for, and then fill in the blanks. So that's how we build this out. Okay, so this is basically going to loop over the outer diameters. It's going to loop over the inner diameters. And for each combination, as we're going through all of those pairings, we're going to calculate the moment of inertia, the stiffness coefficient, and the shaft speed. Then we do a requirement validation. If our shaft speed is greater than our min, we pass, otherwise we fail. And our min is set to 22,000 RPM. Okay, so if our min changes, we change it in one place here, and then we get a new pass-fail matrix. So coming out of this program, we're going to have two arrays. We're going to have a 4x4 array of shaft speeds and a 4x4 array of pass-fail results. So let's scroll down and look at our results. Okay, so on the left we have our shaft speeds. On the right we have our pass-fail results. Let's keep going because right now those numbers don't mean a whole lot to us. We haven't labeled the rows and the columns, so we don't really know what combination of diameters are producing which results. So let's scroll down. Oh, I scrolled a little bit too far. So here, this is this box that we see. Okay, so if you follow my cursor, I'm just tracing the perimeter of this box. This is an area in Mathcad, and that is on the document tab. Okay, and the button for it is here. So as you can see, as we're going through this document, I'm going to the ribbon a lot and pointing to different things and clicking on different things. So as far as learning how to create these documents, it's really, really straightforward. You go to the ribbon, you click on what you need to do, and you fill in the blanks. So this is the area, and that puts in this section with this perimeter around it. And this area can be collapsed if you don't want to display it. Okay, so that's how you protect your intellectual property from reading. Okay, and then if you really truly want to protect it, you can add a password to this area. Okay, and you can establish a password here, and you can lock it in a collapsed state so that people can't expand it. Okay, so this is super powerful. You can protect your IP, you can protect your work, so that when you create your final documents that you're going to publish and share, if you're going to create a PDF file that you need to give to somebody and you don't want them to see anything inside this area, then you can collapse it, you can password protect it. Okay, and in addition to that, if you have certain equations or certain functions or methods or approaches or algorithms that you want to protect, then you can protect those as well. So you can lock this in an expanded state so that people can see what you've done, and they can perhaps even reuse what you've done, but they can't change what you've done. So your formulas and your calculations have to be used in the way that you've defined them and protected them in this area. Okay, so that's what this area is. And what we've done in this area is just some formatting. Okay, so some basic formatting. So we can collapse this so that we don't have to look at it. But you can see that we've added headers to label the columns and the rows. Okay, as well as for the pass-fail table, we've added headers to label the columns and the rows, so we can look at this and we can see, oh, we're failing in the lower right corner at 9 centimeters and 10 centimeters for the two diameters. Now, as far as displaying this and communicating it, we're a little bit limited. So if we go to the math formatting, we can make the entire thing bigger, we can make the entire thing smaller, but we can't do things like conditional formatting. We can't highlight this header going across the top column going down. So in Mathcad, we can display it, and that's helpful. But to make it even more useful, we can take this data and send it into something called an Excel object, and there we can do whatever we want to do with that data as far as presenting it goes. So if we take these numbers and these pass-fail results and send them into an Excel object, we get something that looks like this. Okay, and as you can see, this looks a lot better and a lot cleaner and nicer than what we had up above. So this is an Excel object, and it's basically Excel embedded in Mathcad. Okay, so if we go to the Input-Output tab here on the ribbon, here is the Excel component, and that's what this is. So I'll just come to some blank white space. Actually, I'll go to the next page just to show what this looks like when you create one. So here we are, and we'll click on Excel component, and we'll just start an Excel component. And now we have a spreadsheet object inside our Mathcad document. Okay, so I can double click on it, and it's going to open Excel. And then I can either navigate to an existing file, or I can create a new file like this. Now, whatever we do in this Excel object gets carried back into the Mathcad view. So I'm just doing some simple formatting here, change the color, highlight it. Now, when we close this, what we've just done comes back into the Mathcad view. Okay, and then we can establish inputs here and outputs. So these would be inputs going into Excel. So if we just have a vector, let's just create a vector alpha, and I'm going to go to the matrices and tables and just create a 3x1 vector, and we'll just make it simple. So there's a vector alpha. Now here we can say, going into this Excel object, starting at A1, we want to write in this vector alpha. So alpha goes right into the first column, A1 to A3. Okay, and now let's activate Excel. We have the full functionality of Excel available here on this data set alpha. So I want to make that very clear. We have the full functionality of Excel available to us inside of Mathcad. Okay, so now we have our vector alpha. In column E, we can do something with it. So I can say this is going to be A1 times 2. That's probably not here, 22. Okay, so then let's just carry that down. Okay, and let's maybe make the whole thing a little bit more uniform. So there we go, and we can just center everything there. And let's read out column E. Okay, so those are our outputs, and we'll just make those green. Okay, so now column E 1 to 3. That's what we want to get out. So we'll close this. And then in the outputs, we can say from this Excel object, E1 to E3, we're going to read that out, and we're going to store it in beta. And then we can collapse the inputs, we can collapse the outputs, and we can come underneath, and we can type beta equals, and there's our result. So now if alpha changes, beta is going to change too. So let's change alpha from 1, 2, 3 to perhaps 4, 5, and 6, and now beta is going to update. Okay, so we don't have to activate Excel, we don't have to activate the component to run the functionality that we want to run inside of Excel. Okay, so the point here is that what we've done with this bearing shaft is we've used the Excel component to display these results so that they look really, really good. And we've done conditional formatting as well, because we can do that in Excel. We've highlighted everything green that passes. We've highlighted everything red that fails. So failures are in red, passes are in green. Okay, so we've used Excel to display our data, okay, and make it look worthy of presenting. But we could also use this Excel component to reuse existing spreadsheets that maybe we already have, and we want to just read results out of them and write a report around it, or read data out of it and reuse the actual spreadsheet itself. Okay, so there's a lot of reasons why you might want to do this. But you can integrate with Excel by using that Excel component. Okay, so that's this. So now let's take a look at one more thing here. Okay, so I'm going to scroll down, go past this little ad hoc Excel component. So now we do the exact same thing using functions. Okay, so it's the same problem, but we're doing it with functions. And that means that every function that we define is reusable. Okay, so here, this is going to look very familiar. I is actually a function of outer and inner diameter. So this is similar to f of x. If f of x is a function, then we can evaluate f when x is equal to 6. We can evaluate f when x is equal to 7. We can evaluate f when x is a vector, so maybe something like this. Okay, so f is a reusable function. And what that means is that we define it once, we approve it, we validate it, we have a conversation about it, everybody agrees this is the correct function definition, and then we reuse it multiple times because we have confidence in it, because it's been defined and it's been approved and validated. So that's the kind of thing that might want to go into a protected area too. So here we have a function for I, a function for C, a function for N, and if we scroll down, we solve the same problem using functions. Now here we've created a plot. Okay, so this is a 2D plot in Mathcad. We're plotting the shaft speed, the critical shaft speed on the y-axis. Okay, and we're plotting our threshold here. So that's what a 2D plot looks like in Mathcad. Now this is a basic plot. This is a basic plot. Okay, but we can also create more advanced plots in Mathcad as well. This is a contour plot. Okay, so that's basically the shaft speed as a function of the outer diameter and the inner diameter. Okay, so we can see the diameters going across the axis, the x-axis here, and then across the y-axis. And we can see what those contours look like as far as the shaft speeds go. And then finally, we have our binary pass-fail plot. Okay, so those are basic plots in Mathcad. Now, on the advanced side of plotting in Mathcad, here, let's go back to our ad hoc example here. On the advanced side of plotting, in the latest release, Prime 5.0, we've added a new plotting object, and it's called the chart component. So if we put in the chart component, it looks a little bit different. It actually brings up a charting application, a plotting application. So here we can say if we want to plot the sine of x, we're going to insert the x-axis expression, and that's going to be x. We'll insert a y-axis expression, and that'll be the sine of x. And so then there's our plot. But now, just like we could double-click on the Excel object, we can double-click on this plot object. So if we double-click here, it's going to bring up this charting application. And in this charting application, there is so much we can do to customize the look and feel of this plot. We can also add a secondary y-axis using this charting application too. So if we wanted to go simply on the chart itself, we can add a border around the plot. We can make it pretty thick. We can anchor the corners if we want to. So maybe we want to anchor them a little bit more heavily. We can fill in the plot with a color. So here, let's change the color here. And then the inside of the plot, we can give a different color. So there are a lot of options in here, okay, a lot of options. And then if we go to the x-axis, we can customize the look of the x-axis. So if we want that x-axis to be a lot thicker, we'll make it thicker. We can control what these tick mark values look like, okay, down here. So if we want those to be bigger, we can make those bigger. So we'll make them a 10. And then this is really neat too. We can angle them to the axis. I like this. So if we go to 45 degrees, they're going to go at 45 degrees to the x-axis, and we can also drop them down and give ourselves a little bit more space to the axis. So we've done that for x. We can do it for y as well. So we can make the y-axis thicker and basically do all of the same things. Now, one of the things that I think is worth mentioning is we can add grid lines. So on the x-axis, we can add, go back to x and go to the grid lines, and we can activate the grid lines, and we can, of course, change the color, and we can change the thickness and change the style. Okay, so now this is new. Oh, that's probably not a very good color. This is new in Prime 5. Okay, all of this, everything that we're going through now is new in Mathcad Prime 5. So if you have Prime 4 or 3 or even before that, you're not going to be able to see this. Okay, so this chart component, it's new in Prime 5. Now here we've created grid lines. Those are major grid lines, but we can also do minor grid lines and minor tick marks. And then we would do the same thing for Y. We'd add the grid lines, we'd make those green, probably make them thicker, and we have the minor ones too. And then we can give our plot a title. Oh, sorry, I'm on the Y-axis title. So we can give the Y-axis a title, okay, nominal response. And we can customize what that title looks like, the font, the color, the style, the size. So for those of you that have used Mathcad before, you'll know that we couldn't customize the fonts and the styles and the sizes and the look of the text inside the plot individually. Okay, so now we can do that. So we can make that, bold and change the color. So then if we go to the 1, that's our first trace. We only have one trace. We only have one curve, and that's it. So here we can make that look thicker and do whatever we need to do here. Okay. Now, what we want to do next is just go to the basic chart here and give it a title. Okay, so we'll just give it a title. And so sine wave, and we can position it at any of these preset options. So we'll go above, and then we can also make that different font and so on. Okay, so I don't think I changed anything there. There we go. Okay, and so that's the idea here. Now we can put a box around that as well. Okay, so we can pretty much put a box around anything we want. We could put a box around the y-axis label, the x-axis label, the legend. We can border anything we want in these plots pretty much. So that's it. Okay, so that is new in Prime 5. Now when we close this, let's close it. What we are previewing here is going to get displayed in the Mathcad document. Okay, so there's our plot. Now we can close the inputs, and there's our plot. If we want to change it, we double click and we make whatever changes we want. And if we want to add more data, then we add more data here. So we can add a cosine curve too if we wanted to. So we'd add another x-axis independent variable and then add another y, and this would be the cosine. Okay, so now we're going to see the cosine added. So you can see here it's added. Now we would activate the chart object to go grab that cosine curve and probably change the color of it and so on. So again, that's the chart component. Okay, it's new in Prime 5. So in Mathcad, you can create the simple plots that we looked at. We looked at the plot of the shaft speeds. Okay, and then you can create the more advanced plots when you need to using this chart component. Okay, so I think that's Mathcad in a nutshell. Let's go to how this works with Creo. So I am going to bring up Creo, and what I have here is a model, pretty simple model of a drag brake for a missile or an aerospace vehicle. Okay, so this is a drag brake, and you can see these are the brakes. Okay, so there's 9 brakes, and these brakes have a certain diameter, certain cross-sectional area. And what we're going to do is use Mathcad to calculate the cross-sectional area or the diameter of those drag brakes, and then update this geometry. Okay, so in Creo, under the applications, there's a button here to install a Mathcad worksheet that goes with this model. So we'll click on this. I've already done it, so I'm going to show you where it is. It's right here. And so here you can insert a new worksheet or remove a worksheet. Okay, so we have a worksheet already installed. And when you insert a new worksheet, you're going to see it in the right-hand corner, upper right-hand corner here. So my cursor is over here on the upper right corner. And so that's how you know that this Mathcad worksheet is installed with this model. Now, we've been talking about embedding things a lot. We embedded an Excel object inside Mathcad. We embedded a charting object inside Mathcad. This is we're embedding Mathcad inside Creo. Okay, so Mathcad is inside the Creo file. It's inside the model. It's stored with the model. It travels with the model. It checks in with the model, checks out with the model data. So anytime we want to look at this Mathcad worksheet, we double click here and it's going to open it in Mathcad. So let's look at it. I'm going to double click, and this is the Mathcad worksheet, okay, that we've connected. So here we are going to, let's just walk through it. It's very, very straightforward. Okay, we have some inputs, the altitude, the velocity, the drag coefficient, ISO temperature, and ISO lapse rate. Okay, everything is with units. And then we calculate a couple things here. Okay, and finally, what we want to do is calculate the cross-sectional area of those drag brakes that we talked about. Okay, so here's the force, drag force, 2,800 newtons. That's the maximum allowed drag force. There's a 2D plot. Okay, that's one of the basic plots. And so if we continue to scroll down, here is our final cross-sectional area of one drag brake, 324 inches squared. And then we do a Mathcad program to do a checking validation on that. Okay, is that brake area acceptable or not? So we check it against A min, okay, and A max, and then we can see if it's acceptable. So if it's acceptable, let's send it to Creo and update our geometry. All right, so what we're going to do is change an input here. So let's go back to the top, and let's change the coefficient to 0.5. We're done. Now we have a new cross-sectional area, 132 inches squared. So we're going to push this over to Creo. So we're just going to click on Save and Push. It tells us we pushed it over to Creo. We'll close this. And now we're going to update this geometry. So we're just going to update our geometry, regenerate this model. And if you look at these inputs or these drag brakes, you're going to see the diameter of those drag brakes change. So let's regenerate now. Okay, so there it is. So that change came from the calculated cross-sectional area from Mathcad. And you can see, so we've done some annotations here as well. So that's how we do that. Now, if we want to change it again, we go back here. We can change any input in this document. We can change anything. We can change the calculations. We can change anything we want. Here, I'll make this 0.3, and then we can just save it. And there's keyboard shortcuts for all of this stuff. We don't have to be clicking on this ribbon all the time. I'm doing it so that you can all see what I'm doing. And then we can update this again, and the size of that will update. Those diameters will update again. So there's a little bit of configuration involved here, which I didn't go through, but it's very, very straightforward. It's all documented in the Creo help. But basically, we come under Applications, we install a Mathcad worksheet, we write up our calculations, and then we connect results from the Mathcad worksheet to parameters in the Creo model. Everything goes through parameters. So if we go through the tools and we go through parameters, you can see all of the parameters that have been connected here. So the whole diameter, they're all in here. Okay, so everything goes through the Creo parameters. And And then we also go into relations as well to pull out from the parameters the mapping of the parameters to actual dimensions on the model. So that's standard Creo stuff. So that's how we set this up, and that's how it works. And we can go the other direction as well. We can change parameters in Creo, send them to Mathcad, send anything we want from the model to Mathcad based on a change to a parameter, and then have Mathcad do a check and validation to make sure that our design is still adhering to the requirements. Okay, so I want to stay on track as far as the time goes. We covered a lot of information. I hope that this was informative. I hope it was helpful. I'm going to transfer control back over to Stuart to manage any Q&A that has come up, and then also to close out the webinar. But I want to thank everyone for joining today. Thank you for your time. Thank you for joining. Thank you for your interest. And Stuart, back over to you.
Thank you very much, Angie. All right, I will just share my screen here, just as a quick reminder for everyone. And wanted to give everyone a chance to ask any questions. So if you do have any questions, you can go ahead and put them in the chat window, and I'll read them out. Or everyone is muted by default, but if you did have a question, please go ahead and unmute yourself and ask about that. I did get a question earlier that someone was saying we were looking to see the relation between Mathcad and Creo. That did come in before Angie got to that, so I hope that question was answered. But if anyone has any other questions, give you guys just a moment to ask. And I will also send out an email as a follow-up, so you can ask any further questions. And again, the current promotion of 35% off is this week only. So if there is interest, please contact me. I have my contact information right here, and you can go ahead and contact me anytime. All right, well, I don't see any other questions coming in. So again, please feel free to reach out to me if you have questions about either the sale, or if you have any technical questions. If I can't answer it myself, obviously I'll contact Angie, since she is the expert, as you just saw. So Angie, thank you again for the presentation today. I think that was very useful. It's always great to see the new features. And thank you everyone for joining and for the time.
Thanks, Stuart.
All right, well, have a nice day, everyone.